We are going to show in this lecture that the subset of the set of CR maps between two differentiable manifolds is an open set. The proof is a little bit trickier than it is for immersions because immersions have a nice property. Indeed, if a map is an immersion in the neighborhood of every of the points of its domain of definition, then it is an immersion. This property is not true. The analog of this property is not true for embeddings. We could have a map that is an embedding in the neighborhood of every of the points of its domain of definition, but that is not an embedding. And so, as a consequence, we have to be a little bit more careful when proving that the set of embeddings is an open set. What we want now is to see that the set of embeddings is also open, and this is a little bit more complicated. Okay. First of all, we would like to consider a local result that is the following. At some point, we should actually consider expressions of our differentiable maps in local charts, and in that way we obtain differentiable maps between open subsets of Euclidean spaces. Okay, so consider here a CR map from an open subset U of Rm to Rn, right? And now we are going to consider W an open subset of U such that the closure of W is also a compact subset of U. Suppose that F is an embedding. Okay. And what we would like to see is that if we deform very little both the values of F and the derivatives of F, then the map is still going to be an embedding in the neighborhood of the closure of W. So what we would like to see is that there exists, a positive real number such that if we have that the differential of F minus differential of G, okay, let's say K, it's smaller than delta for every X in the closure of W and K in 0, 1, and obviously G is also a map from U to Rn of class CR, then what we get is that G is an embedding in a neighborhood of the closure of W, right? We're not going to prove this result because indeed we already did. Okay, what we know is that G is going to be an immersion in a neighborhood of the closure of W because of the openness for immersions that we already proved. And the main problem here is showing that G, if it's sufficiently close to F, continues to be injective. But we already did this proof. When we consider stability properties in lecture 15 by using the homotopy point of view, at some point we needed to show that embeddings defined a class of stable maps for differentiable maps defined in a compact manifold. Here, by repeating that proof, you can check the proof out, we can prove the result in red. Because even if M is not compact, the closure of W is, and so the proof works the same. I repeat that this is a result that it is of local type. The one thing that we are going to be able of doing with this result is going to local charts and proving that in the neighborhood of some compact sets, small perturbations of F continue to be embeddings. Okay? Now, let's continue the proof by assuming this local result. Let F be an embedding. And now we want to find a neighborhood of F that consists uniquely of embeddings too. Okay, so let's consider an atlas of M such that the family of the domains is locally finite. Okay. Moreover, we can assume, that the image by F of every UI is contained in some WI, okay, where we have a local chart defined in that WI. This is doable. We just, if we consider an atlas that does not satisfy this condition, we can consider a smaller domains UI. We can always get to this situation. So we have the two set of local charts, the phi, the psi. We have to define the family of compact sets. And so we are going to define a family Ki. Okay, family of compact subsets of the manifold M such that Ki is contained in Ui for every I, and moreover, the union of the Ki's is the whole manifold. We can do that too, right? Indeed, we can consider there exists an open subset Wi of Ui such that Ki is contained in Wi, which is contained in the closure of Wi, which is contained in Ui, and this set over here is compact, right? We can do that. And now we are in the situation of the local result, because if we consider the expression of F in the local charts phi sub I and psi sub I, this is defined in the image by phi sub I of U sub I. And in particular is defined in the image of the closure of Wi, which is a compact set. So we have now a map between open subsets of Euclidean spaces that is defined in the neighborhood of some compact set, right? If we consider now a very small epsilon I, what we want is defining here our family of positive constants, but by the local result, if epsilon I is small enough, what we get is that f f is sorry, what we get is that g. Sorry. If we can consider this set over here. Okay, with our families of local charts for M, local charts for N, the family of compact sets of the manifold M, and the family of constants. And what we get is that if epsilon I is small enough, then every G in this N super zero satisfies that is an embedding in a neighborhood of the closure of WE, of that compact set that contains the compact set Ki. The issue is that we cannot finish the proof here just right away, because it's not necessarily true that if it's an embedding in a neighborhood of every of these compact sets, it's going to be an embedding in the, it's not necessarily true that it is an embedding in the union. So we need to work a little bit more, right? But this set is actually going to be important in the proof. Something else that we see is the following. There exist open subsets AI and BI of the manifold N such that the image of Ki is contained, in AI, and the image of M minus Wi is contained in BI, right? It's clear that by construction, there are open neighborhoods. Of course, there is some property missing, and it's that these sets are disjoint. Otherwise, this is not interesting at all. But this is very easy for Ki and the complementary of Wi, because Ki is contained in the open set Wi. And since F is an embedding, and in particular a homeomorphism with the image, then it's also going to be true for the images. So we're going to be in this situation, okay? What happens here is that now we can define another set. We can consider the CR maps from N to N such that the image of Ki is contained in AI and the image of M minus Wi is contained in BI, right? And what happens is that this set is indeed also open for the strong topology. It's not difficult to check it out. So this is an open subset of, is that over here, all right? What happens is that we actually can consider the intersection of both of them. By construction, F belongs to both of them. Here is obvious because F satisfies these conditions. Of course, this is a condition for every I. So what we want to prove now is that every element of this open set is indeed an embedding, because if we are able of showing that result, it's over. We proved that there exists a neighborhood of F that consists just of embeddings, right? So we are going to prove that. Very well. So we consider a map that belongs to the intersection of these two sets of maps, right? The first thing that we want to prove is that G is indeed injective. Okay, let's see if let's see what we can do. So suppose that G of X is equal to G of Y. Right. What we know is that X is going to belong to some Ki, because the union of the Ki's is the whole M. So there exists some index such that X belongs to Ki. Okay? In particular, since G belongs to n super 1, that implies that G of X belongs to AI, right? By definition of this set of maps. Very good. But since the image of X by G is equal to the image of I, that implies that G of I belongs to AI. Okay, and we know that if G belongs to n super 1, the image of M minus Wi is contained in Bi. And we also know that AI and Bi are disjoint. So in particular, that implies that Y belongs to Wi, right? And so X, because Ki is contained in Wi. But the restriction of G to a neighborhood of the closure of Wi is an embedding, so in particular injective. Here we use that the restriction of G to the closure of Wi is injective. And so X is equal to Y. And so G is injective, right? So we have the first property. We want to prove another property, obviously, is that G is a homeomorphism, right? It's a homeomorphism between M and its image. But okay, G is injective, so we have an inverse map. And what we want to show is that if Xn converge to X0, Okay, and all these elements, or I don't know if xn is the first, we can actually consider here maybe yn, y0, okay, and yn belongs to the image of n for every n, and also y0, okay. What we have to see is that when we apply the inverse of g, the limit of the preimages of the yn converts to the preimage of y0. Okay, let's see if that's true. So let's denote the preimage of yn by xn and the preimage of y0 by x0, right? Again, now all these points, xn, x0, are points of M. So there exists some index such that x0 belongs to ki, because the union of the ki's is the whole M, right? And in particular, the image by g of x0 belongs to ai. And here we are using again that g belongs to n super 1. AI is an open set. So since g of x0 is y0 and theyn's converge to y0, that implies that yn for n big enough belongs to ai. So yn belongs to ai for every n big enough. But again, we know that the image of the complement of wi is contained in bi, right? So yes. So that implies an ai and bi are disjoint. So this implies that xn belongs to wi for n big enough. So all the xn's for n big enough and x0 belong, all of them, to wi. Okay, so xn belongs to wi for all n big enough, and x0 belongs to wi too. And what we want to show is that the limit of the xn's is x0. That's the end of the proof. Okay, because what we had initially, okay, let's initially we have that the limit of yn is y0, and we want to prove that g minus 1 is continuous. So the g minus 1 applied to yn is xn, and g minus 1 applied to y0 is x0. So we just have to prove that the limit of xn is x0. It's everything that we have to do. But we can use now that G defines an embedding in the neighborhood of the closure of Wi. So since we have this property over here, it is just saying that the limit when n tends to infinity of g of xn is the is the image of X0, and G is an embedding, in particular is a homeomorphism between the closure of Wi and its image, that implies necessarily that the limit when n tends to infinity of xn is equal to x0. And this proves that the inverse map is continuous, so that G is a homeomorphism. And in particular, what we got is that if G belongs to n super 0 intersection n super 1, then G is an embedding. So we found a neighborhood of F of an embedding which consists only of embeddings. And in particular, we get that the set of embeddings is an open subset of the set of CR maps for the strong topology. Today, we proved that the set of embeddings is an open subset of the set of CR differentiable maps between two fixed differentiable manifolds. In next lecture, we are going to see that proper maps, closed embeddings, and diffeomorphisms define also open subsets of the set of CR maps, always for the strong topology. Thank you for your attention.